solve some problems and new problems will emerge. So I think it'll be a long time before we see self-driving cars, in rural Colorado, say, for reasons we can talk about. But mapping, the work that Uber does here and the work Uber does in Pittsburgh, is really, really important to autonomous vehicles. Mapping turns out to be really expensive because you have to keep the maps up to date, and particularly in rural America, the economics or rural anywhere, the economics are tough. And as we getting self-driving cars to other countries will be challenging. Building out kind of infrastructure. The hope is that we'll build out infrastructure for self-driving cars as they kind of come online, and there'll be things we need to do to take advantage of vehicle-to-vehicle communication, potentially special self-driving car lanes or roads. So I see this going on for quite a while, and even after, maybe then I'm time to retire by hopefully I'm ready to retire by the time it becomes a solved problem. But I would imagine, much like mobile phones, there was like a lot of work in getting just like something like an iPhone working. But after that launch, there were all sorts of applications related to apps. And the skill sets change a little bit, but skill sets are always changing. That's kind of why people take online courses at places like Udacity, or they go back to school, or just as you work, you learn new things. And so I see this as an industry that will be really, really important.
So cars have been around for over 100 years, and cars aren't done by any stretch of the imagination, even the mechanical parts.
Excellent point.
Yep.
That's probably more. That's a much more concise answer than I gave, and probably a better answer. But that's absolutely right. Yeah.
How does Udacity work with like employers, like with our projects and stuff? Like.
Yeah. Great question. So the question's about how Udacity works. Particularly in the self-driving car program, we have all these hiring partners. We have over 30 now. I think we're about to do a big announcement for a bunch more big employers that we're working with to help place students. So this hiring partnership thing is a little bit of a work in progress. We kind of invented it on the self-driving car program, and not entirely, but we are figuring out how to scale this notion of having hiring partnerships with companies and getting students to them. So what we do right now is we have a team that works with recruiters at each company. So we work with a recruiter at Uber ATG in San Francisco. We work with recruiters at Fiat Chrysler, at Here, at NVIDIA, at Mercedes-Benz, BMW, lots and lots of companies, big and small. And we try and match students we have to their openings. And kind of the first pass on this is we have Udacity Hiring Partners Jobs Board. Have any of you all visited the Hiring Partner Jobs Board? Does it seem familiar to a few people? So as you finish term one, if you're not finished with term one, you should hopefully get an email from our careers team pointing you in that direction. And that's a place where we post jobs that our hiring partners are looking to fill. And the first step is just to ask you, are you interested in that job? And then we send over lists of students who are interested in those jobs to the relevant employers, and we try and help the employers sift through which students might be the best match. Right now, that's a little more ad hoc than we'd like, and so we're trying to systematize it through a few different ways. We're looking at maybe doing kind of extracurricular projects specific to certain companies, maybe using a little bit more machine learning, you would imagine, to try and like match students. That's always really hard to kind of match students with employers. So right now it's kind of manual. We have one recruiter in particular. His name's Mark Gentry. I don't know if any of you all have met Mark. He's on the Slack channel. Okay. Mark's whole job is to match students with employers, and then we have a team that kind of interacts with the recruiters that are our hiring partners. So that's how the hiring partnerships work. Cool.
Okay. So hi everyone, welcome to Autonomous Denver, your local self-driving car meetup. I'm Nate Swanberg, and I'm one of the hosts along with Aaron Smith. And we meet regularly, once a week, to work on the Self-Driving Car Nanodegree. And then we meet semi-regularly when we have a speaker like David Silver in town. We've also had a couple of other speakers, including Gina Kim, who's here in the audience, who gave a talk on segmenting brain images into tumor and not tumor sections using deep learning. So we'll continue to have these. Let's see, we have just a couple of announcements. We don't meet just to study for the Nanodegree, we also meet to work on projects together. So I think Jacob Thalman was talking about doing a project with examining his own car's CAN bus. So anything from that. SparkFun, a local electronics seller in town, also has an autonomous vehicle competition. So abc.sparkfun.com. You can look that up, and if you're interested in entering, I think a few of us in the course want to compete in that. You can see more details there. And so with that, we're already running a little bit late, so we'll get started. Again, we've got David Silver, an instructor at Udacity, and he's going to talk about Udacity's self-driving car that they're building. Thanks.
All right. Thanks so much, Nate. And if you all can keep me kind of in line with the camera, I have a tendency to wander. My name is David Silver. I do work on the self-driving car program at Udacity. It's a 9-month program that covers the autonomous vehicle technology stack. I'll talk a little bit about that, and then mostly, as Nate said, about the Udacity self-driving car. First, I should just say how delighted I am to be in Denver. I landed this morning. I'll be here in Colorado for about a week. I'm not from Denver. I'm from Virginia. But my father went to law school at DU, and he had Broncos season tickets in the 70s. My brothers and I grew up watching Broncos games. We are rabid Broncos fans. I'm excited to see if they can do a little better this year. Excited to see who they start quarterback. So it's nice to be here. I always love coming to Colorado. So this is Carla, the Udacity self-driving car. That's her name. Carla is a Lincoln MKZ. Lincoln is Ford's luxury brand. The MKZ is kind of a step up from the Ford Fusion. And we bought Carla from a company called Autonomous Stuff. Autonomous Stuff is an Illinois-based company that takes Fords and turns them into drive-by-wire machines. So I was mentioning to some people earlier that Autonomous Stuff delivered the car to us, and they handed us a PlayStation controller, and they said, look, you can drive the car with a PlayStation controller. And lo and behold, we could drive the car around the parking lot with a PlayStation controller. And they said, if you can drive it with a PlayStation controller, you can program a computer to drive it. So they didn't do the self-driving stuff, they did the kind of drive-by-wire stuff. So that's our self-driving car. We've been working on it since last fall. We had a team of folks working on the car that made so much progress actually that they spun out and formed their own company called Voyage. They're building robotic taxis. I'm happy to talk more about what they're doing in the Q&A. Some of the work, a lot of the work I'll be talking about today is stuff they did, and those of us who are kind of more focused on the Nanodegree program have kind of taken over the project and are preparing Carla to run student code as students finish the Nanodegree. That's kind of the highlight of the program. I'll tell you a little bit about the Nanodegree program to begin with, and then we'll dive into Carla, and then we can spend most of the time just talking about whatever is interesting to you all. So this is the Nanodegree program. It's 9 months. Each month covers a different topic. The first month or so is an introduction, kind of a high-level overview of self-driving cars and how they work. The next month covers deep learning. We built that out with our friends at NVIDIA and also Uber ATG. And students learn about how to use deep neural networks to do things like classify traffic signs or even teach a car to drive. The third month is computer vision, kind of more standard computer vision techniques for doing things like lane detection and obstacle tracking. The fourth month is something called sensor fusion. So sensor fusion is how we take radar and LiDAR and other sensor data and fuse it together to get an understanding of what the world around us looks like. So, for example, if a radar tells you that a vehicle is over here and a LiDAR says that there's a vehicle over here, we want to know how do we fuse that data together over time to get a sense of, is that one vehicle, is that two vehicles, what is that vehicle doing, and where is it over time? So we built out sensor fusion in collaboration with our partners at Mercedes-Benz. They have a terrific sensor fusion team that, that helped us build out some pretty advanced algorithms and projects for students. We also worked with Mercedes-Benz on localization. So localization is how we figure out where we are in the world, and that might seem pretty straightforward in a world with GPS. You know, we drive around, we we kind of know where we are all the time. But if you think about a self-driving car, GPS is only accurate to about 1 to 2 meters, so about that much. And if you think about that much accuracy, if you're off by that much and you're in you're in 14th Street in downtown Denver, it could be pretty bad. You could be off on the sidewalk hitting things. You wouldn't want that. So we use more sophisticated algorithms and maps and sensors, something called a particle filter, to figure out where we are to within single-digit centimeter level precision or accuracy. The 6th month is control. This was built out again with our friend Drew Gray at Uber ATG. Drew did his PhD in control. He now actually leads part of Uber's deep learning team, but he came kind of back to the good old days of control. To his past, control is still a very relevant part of autonomous vehicles. It's just not what he works on now. Control is how we move the vehicle through space, how we actually hit the gas, hit the brake, turn the steering wheel. And so if you think about executing a left turn, I'm reasonably good at that now. If I turn too hard, I kind of ease up, or if I need more gas, I hit the throttle. Teaching a car how to do that is actually a little bit difficult, and we use different algorithms called controllers to kind of help follow a trajectory and figure out how to actuate the vehicle or apply the gas, the brake, the steering wheel to follow a trajectory. So that's the portion of the program that's been released so far, the first 6 months. We are coming up on in the next week or so in releasing the next 3 months worth of content. So I'll run you through kind of what that's going to look like. That might be interesting to some of you who are approaching what we call term 3. So the first month of term 3 will be path planning, built out with our friends at Mercedes-Benz. So I'm going to move just so I'm out of the light. Path planning is how we decide where to go, both at the micro level, or sorry, at the macro level, how do we get from here to there, and also at the micro level, what do we do if say a cat runs out into the road? How do we build a trajectory? Then in the 8th month, there will be an elective month to kind of go deep in different areas. We're launching with a couple of electives, and we'll build out more over time. The 2 electives we're launching with our advanced deep learning, where we'll cover semantic segmentation. So that's taking pictures of the road and painting different pixels, different colors, depending on what they represent. So maybe one color for the background, one color for the road, one color for pedestrians, a different color for vehicles, and using deep neural networks to do this. This is really kind of the cutting edge in deep learning for perception and autonomous vehicles, and it's really exciting to be able to work with NVIDIA, which is one of the world leaders in deep learning on a project like this. Another elective is functional safety. So this is kind of more core automotive engineering. How do we build vehicles that are safe? And this is actually an elective where we kind of cover a lot of what is it like to work in the automotive industry, what types of roles do people have, and how the development cycles in the automotive industry work. So those are the 2 electives. And then the final month, which kind of segues nicely into the overall talk, is system integration. And this is where we're having students actually put code on the car. And so we've studied all these different parts of an autonomous vehicle, and in the final month, students get to form teams and put their code on the actual Udacity self-driving car, on Carla, and see how it does. And we think of this as kind of an exciting only at Udacity kind of thing, that we have our own self-driving car, and as part of the program, students get to put code on it. So that's the program. I'm happy to answer more questions about it later, but I'll just move on and run through a few slides on how Carla works. So this is another shot of Carla, just so you know what she looks like when she gets a good photo. I'll start by talking a little bit about what some of my colleagues, the folks who were working on the car last fall did. They set this goal for themselves to drive from Mountain View to San Francisco on El Camino. I'm actually not familiar enough with Denver, unfortunately, to know what the equivalent of El Camino is. If anybody knows, they can shout it out. But it's like varies between like a 4 and 6 lane commercial road that kind of runs straight up Silicon Valley. And Sebastian kind of said, you know, you guys should be able to get up El Camino in 4 months. And I kind of thought, there's no way that happens. And it didn't happen. It took them 5 months, but they got it. I was quite impressed. And so they drove that route from our office in Mountain View to the San Francisco border. And this is some sensor data. You can see both LiDAR data. You can see kind of what's going on with traffic lights, because it's this commercial road that has a ton of traffic lights. And you can see camera data. They did a bunch of different runs. This is one of the runs. The first run they did was at like 2 in the morning, and we said that doesn't really count. Like, you drive at 2 in the morning, there's nobody else out. So then they did it like, you know, in rush hour, and you know, everyone was suitably impressed. So there are kind of 3 main blocks to how the Udacity self-driving car works. There's a mapping block, a localization block, and a perception block. So the mapping block is surprisingly important. You need a high definition map to really be able to localize the vehicle. So we talked about this a little bit in the Udacity self-driving car program with particle filters. Essentially, the way that Carlo works right now is the car takes a really high definition LiDAR map that in some cases we're able to build the map ourselves. In other cases, like on El Camino, which is a really dense, tough to map area, we actually pay a specialty mapping company to come out and build the map for us. And then when Carla drives through an area, it compares what the LiDAR on the top of the car sees to the map, and uses automotive middleware. So there are a couple of big open source automotive middleware packages we use on the car. One's called ROS, Robot Operating System, and another is called Autoware, which kind of sits on top of ROS and has some higher level functions. And we use the Autoware block or the localization block in Autoware to basically run LiDAR data into Autoware, and then Autoware kind of spits back based on the map, here's exactly where you are. So we need that high definition map. Then we run through and we perform localization. And that's basically how the car kind of moves from point to point through space and figures out where to go, is it just kind of follows waypoints. But then the final block is a perception block, and that's for doing things like obstacle detection, traffic light classification, figuring out the parts of the world that aren't on the map and how to react to that and how to drive around that. So for each of these blocks, I talked a little bit about mapping already. Some of the big challenges with mapping are particularly areas where elevation changes. That makes mapping really tough, at least high definition mapping. So when you start to go up hills or when you go under an underpass, it can get a little confusing. Is the road ahead of you, like, you know, it looks different if it's flat than if its elevation is changing. And you know, one of the interesting stories actually that Sebastian, my old boss, or my current boss, who used to be the head of the Google Self-Driving Car program, Sebastian has the story about, or kind of thing he learned at Google, which is they would drive 101, which is kind of like the main highway through Silicon Valley. It's kind of like I-70 maybe, and as the Google Self-Driving Car project was like mapping 101 and driving 101, Sebastian says the entire map of 101 would basically turn over and be completely different every 3 months, because Caltrans, the Department of Transportation, is basically out repaving some part of 101 every single night. And so over the course of about 3 months, pretty much the entire map changes. And that's part of what makes self-driving cars so difficult to roll out, or the grammar's not correct. That's part of why self-driving cars are difficult to roll out in large areas right now. So if you think about where self-driving cars are now, Uber is testing them in Pittsburgh. Google's testing them in a kind of small area of Phoenix. A couple different companies are testing in Singapore. And there are some other areas that they're supposed to roll out in the next 6 months to a year. And one of the reasons these geofence areas are so small, Singapore is a very small city-state, Pittsburgh, relatively small, part of Phoenix, relatively small, is mapping is really, really hard, and keeping up-to-date maps is expensive. And that's one reason we'll see these kind of level 4, level 5 vehicles probably come to urban areas faster than we will see them come to rural areas, because in urban areas you have the density and the economics to support lots and lots of mapping. So that's the mapping component of the Udacity self-driving car. This is the localization component, so you can see kind of a video of our car driving through space, and essentially what's happening is as it drives through space, it is able to match what it sees with its LiDAR to different points on the high-definition map it has on board. And so essentially it's kind of figuring out where it is and seeing more of the world as it goes and verifying, step by step that it is where it thinks it is. And you can see kind of an illustration here of kind of GPS versus LiDAR, kind of the level of accuracy. GPS is, a meter or two, kind of this big halo around the vehicle, like kind of think you're in the right lane, but you don't really know for sure. Whereas with a LiDAR and high-definition mapping, you have really, really super high precision.
Can I ask you a question about the state of practice?
Sure.
So when I'm driving, right, I just have the map and I'm creating that localization and doing that navigation on my own without having a high-res map. So is the state of practice that you need the high-res map to sort of tell which lane you're in and exactly where you are, or is not that you're just figuring that out from GPS and then just sensing around, okay, I can see the curve here and other cars there, so I know where the lane is?
Yeah, great question. So the question is the current state of the art using these high definition maps, or are we getting to the point where we can kind of figure out what the world looks like, or the computer can figure out what the world looks like as it drives, kind of the way humans do. Humans don't need super high definition maps to figure out the world. So the current state of the art is primarily using high definition maps. There is some amount of what's called SLAM, or simultaneous localization and mapping, which is where you kind of drive around in an area that you don't really know 100%, you kind of figure out where you are simultaneous to going through the area. SLAM is really, really hard, particularly with kind of our current sensor suites. There are a couple of issues. One is that the algorithms for figuring out what the world looks like around you are not quite where we would want them to be to rely entirely on SLAM or on figuring out where we are. A lot of companies like our partners at NVIDIA are working on deep learning algorithms to kind of figure this out without maps. And there are a bunch of Silicon Valley startups that are kind of trying to figure out, can we do this with deep learning or with other machine learning algorithms and kind of figure it out as we go and not be so reliant on maps. Tesla is probably the most famous example. Tesla does not use LiDAR at all. They use primarily cameras with a little bit of radar. And you kind of see this interesting kind of dichotomy between companies, mostly Tesla, but companies like Tesla that are doing kind of vision-based systems and trying to figure out the world as they go, and companies like most OEMs, most automotive manufacturers that are using LiDAR. So Tesla operates best on the highway, very structured environment, kind of easy to figure out where the lanes are, what traffic's doing, no intersections. Whereas companies that are using LiDAR tend to work really well in urban areas where the economics of mapping those urban areas work really well. And so there's kind of this race as Tesla kind of builds out its vision-based system. I mean, other companies build out their kind of LiDAR and mapping-based systems. Will the algorithms get better to kind of do SLAM and figure out where we are first, or will the cost of LiDAR come down so low that it like becomes a lot more economical? That's one of the big hurdles to using LiDAR, is it's really, really expensive right now. Thanks.
So,
yeah.
The point cloud you showed here has come from LiDAR.
Yes. So this is
the point cloud.
Yeah, this is the LiDAR point cloud.
You never use any images to generate this point.
Right. So the current setup, the tech stack for Carla, does not use images for localization. It's all based on LiDAR. It's kind of just driving kind of something it's seen before, something the map has, and figuring out where are we on the map and kind of following waypoints around.
So why not using images?
So it can be really tough to combine images with LiDAR data. It's actually easier to combine radar data and LiDAR. Although we would like to use images, that's kind of where we'd like to get. One of the things that is notoriously difficult right now with images is distance estimation. So we can kind of figure out where a landmark is, or that a landmark is there, but figuring out precisely how far away it is with a camera turns out to be really, really hard. With a radar, with a LiDAR, you get the distance estimation pretty much for free as part of the pingback. So it's harder to combine with camera data because you don't have that distance to how far am I from the landmark.
But you never try to combine the image with LiDAR? With
No.
LiDAR, you can get the depth, and with the image, you can get everything. So you combine them, you can get more.
I think that's the goal. I mean, one thing with the image is you actually don't get depth right now.
I know.
Pardon?
If you have several cameras, would it help to figure out the depth?
Right, so that's really smart. So there's actually, you may know more about this than I do, but there have been some interesting research papers published. Actually, Drew Gray at Uber pointed me to one of these most recently about using stereo cameras and the geometry behind stereo cameras to figure out depth estimation. So if you can kind of, if you have two cameras and they're kind of side by side, and you see the same image in each camera, or the same landmark in each camera, and you can match that landmark is the same, you can use the geometry of the cameras to figure out how far away that landmark is and do depth estimation.
That's actually how human eyes.
Right, so there's kind of early stages for that. As far as I'm aware, there's not that much that's not in production yet, and I've heard that there's some difficulty in getting the cameras far enough away that you can really do depth estimation at long range the way you can with LiDAR. But that's like a really interesting idea for how we might get depth estimation. Another interesting idea is simply building big data sets. So companies that are in this space might drive cars around maybe manually with a LiDAR and a camera, and use the LiDAR for depth estimation and the camera for vision, and then combine that information to train neural networks.
That's doable.
That's doable. There aren't public data sets for that yet, but that's not to say that companies aren't doing that privately. But there hasn't been a lot of work published in doing that yet. That's kind of the next frontier is deep neural networks for depth estimation. So, but really, I mean, that's really good questions. Those are this is kind of the cutting edge of using perception for autonomous vehicles. So that segues into perception, which is kind of the last part of how the Udacity self-driving car is built. The goal is to take images like what's on the left, so annotated training data. So basically, just like we were talking about, you might drive around by hand and see different things, and then annotate them, draw bounding boxes around them maybe. It's really common now to use a service like Amazon Mechanical Turk to kind of send out your images to people all over the world, and for relatively economical sums of money, they'll pull the images off and they'll draw bounding boxes around the vehicles and the pedestrians, and then you can use that training data to get to something like we see on the right, which is a neural network or a model that can do classification and vehicle obstacle detection in real time. NVIDIA's done a lot of work in this. Other companies, Raquel Urtusan, I think I pronounced her name right, who just joined Uber as the head of Uber's Toronto office, is really famous for building a data set called Kitty that is used for doing this. So this is kind of the goal. This is not where the Udacity car is headed yet, but this is where everyone's trying to head.
Quick question.
Yeah.
What model did you use for classification?
So I'll skip ahead a few slides. So the only real model that the Udacity self-driving car uses at the moment, we're hoping to kind of build out the deep learning in the car, is for traffic sign classification. So it's just a straight convolutional neural network. We use LiDAR data to figure out where the traffic lights are ahead of time, and then it's almost pixel counting. It's kind of red, yellow, green. What color is the traffic light, and should we stop at the intersection? Our goal is to build out models to do things more like what we see. I don't know if this is YOLO specifically, I forget, but this is a video of one of the many different types of neural networks now that is kind of trained to do obstacle detection for deep neural networks. So that's where we'd like to get to. For the moment, we basically use LiDAR to figure out where the traffic light is. We use radar to figure out where the other obstacles are. So you can see we have kind of a long-range front-facing radar, and then a kind of wider range, but shorter range, kind of wider radar, and that gives us pingbacks as to where other vehicles are on the road, and we can run it through some ROS and Autoware sensor fusion algorithms to figure out if pingbacks match the same vehicle, and basically adaptive cruise control. Should we speed up? Should we slow down? We'd like to get to the point where we could do more path planning, things like lane changes, be a little bit more of an intelligent driver. So we use LiDAR for kind of localization and also figuring out where things like traffic lights are. We use radar for figuring out the other vehicles on the road, and then we use vision right now pretty much only for traffic light classification, although we hope to improve that over time.
How about potholes?
So potholes are part of the map. And if they're not part of the map, that's where problems arise. So, hopefully we can pass over them quickly enough that we can get to part of the map that looks like what we expect it to look like. And of course, things change, and the controllers are built to kind of recalculate paths as you get kind of bumped off track. So it's not a huge problem, but ideally you would have the potholes as part of the map. But they do create all sorts of problems. If we had one thing we can do to accelerate the development of self-driving cars in America is just pave the roads better.
If there's a road detours that happens.
So our cars wouldn't handle that. The safety driver would have to take over. But Google is very, very good at that. So Udacity's offices are only about 3-5 minutes away from the Google self-driving car offices in Mountain View, just across the train tracks, and we see the Google self-driving cars just drive around Mountain View all the time, and they've just gotten so good. Sebastian has all these great videos from his time at the Google self-driving car project about the car like noticing signs that a human wouldn't notice, or kind of anticipating maybe road work that's going on kind of occluded behind another vehicle, but the car can kind of see underneath, the radar can see underneath the parked vehicle, or it can notice other things that kind of cause it to slow down or stop. Some of the work Google has done is really, really impressive in that regard.
So that's more sensor-based than the image-based?
It was at the time. The thing Sebastian has talked about, he has to be careful not to disclose any super confidential or any confidential information. And I haven't pressed him too hard on exactly how the Google car work, other than just kind of the high-level architecture. But it does seem, the Google car does use LiDAR, as does Uber and most vehicles other than Teslas. So they make heavy use of sensors. So that's it. That's the Udacity self-driving car. That's how it works. Happy to field any questions about the car, about Udacity, about self-driving cars generally, about me, whatever. Yeah.
What's Udacity's goal with this car? Is it a hobby for the company, or is this something that you're trying to do something more with?
Yeah. There are kind of a few things. So the most obvious goal is giving students a great opportunity to actually put code on a vehicle. So we talk a lot at Udacity now, but this notion of only at Udacity programs, only at Udacity projects, the types of things that would be really hard for students to be able to do somewhere else that we can help deliver. So this is kind of the definition of that almost. And hopefully this helps students become more employable. That's kind of the ultimate goal of the self-driving car program, is to help students get jobs in the industry, and hopefully being able to go into an interview and say, I actually put my code on a car, and here are the things I learned about, working in real time, about embedded systems by actually putting code on a car. That's kind of the main goal. There's another goal or kind of benefit of it, which is marketing. It's been really good for us from a marketing perspective to have the car. People want to come by all the time and just see the car, ride in the car. So that's really nice. We get to go to conferences and show off the car. So that's really good. And I think Sebastian just likes having a car around too. I mean, he spent his whole life on cars, and then he was at Carnegie Mellon working on cars, then he was at Stanford working on cars, and he won the DARPA Grand Challenge. Then he started the Google Self-Driving Car project, and then he came to Udacity to kind of get back more into education, but now he gets to kind of pull cars into education, and so that's, I think, a lot of fun for him. And a lot of fun for us too. It's like a lot of fun to be able to work on the car. So it serves a lot of different goals, but ultimately it's about the students first and helping students get jobs. Yeah.
Path planning. So what's the state of the practice in path planning and obstacles and avoiding obstacles or solving problem and all that stuff?
So I kind of elided, that's a really good question, and I kind of elided that in our conversation because the Udacity car does not really have much in the way of path planning. Basically, the Udacity car can follow waypoints that we've already driven. So if we drive from Mountain View to San Francisco by hand, the Udacity car can kind of follow that on its own. It can, it can do that as many times as we want, but it can't necessarily go somewhere that we've never gone before. Just by
not changing lanes then.
Not changing lanes. We drive it into the lane, we hit the button, we let go, which is still pretty impressive, but it's not the same as being able to pull out of its parking slot and get onto the road and just go. So path planning, the question's about path planning, what the state of the art is. We actually were about to launch the path planning module in the Nanodegree program. Path planning, at least as we teach it, kind of has, and Mercedes-Benz teaches it, has kind of three distinct parts. The first is what's called prediction. So that's predicting what the vehicles around us are going to do. So you think about driving on the highway, you see these other vehicles, and you're trying to figure out who's about to switch lanes, who's about to slow down, who's about to speed up. And that leads into the second part, which is called behavior, and that's deciding our own behavior. So we know what the world around us looks like, we know where we want to go, we have these ideas, these predictions about what we think other cars are going to do, so what should we do? Kind of at a high level. Should we shift lanes? Should we go straight? Should we slow down? Often those are built with what are called finite state machines, which is kind of a fancy way of basically saying you have like maybe 7 or 10 options. Like, you can shift lanes right, you can shift lanes left, you can slow down, you can speed up, you can do a few other things. And you have to pick which of those you want to do. And that leads into the final part of path planning, which is trajectory generation. So if you want to shift lanes, then you have to figure out what trajectory do you actually want to use, because if there are cars around you and you pick the wrong trajectory, maybe you collide with another car, or even if there are no cars around you, there are a lot of different trajectories you could pick to change lanes, and some of them will be very jerky, and some of them will be smoother, and you want a smoother trajectory. And so you kind of go through prediction, then behavior, then trajectory generation, and ultimately you have a trajectory that you can then pass to the controller, or sometimes called the motion controller, and that's what actually hits the throttle, hits the brakes, moves the steering wheel to follow the path. There are some more advanced things you can do with path planning, but finite state machines are kind of the consensus for published state of the art. There are a lot of different kind of proprietary techniques OEMs are using to try and improve on that, because path planning can get really messy in urban areas when you have a lot of different things coming at you and trying to predict what 100 different pedestrians or cars are going to do. But that's kind of where the state of the art is today.
It's part of the appeal of the finite state machines being the fact that you can choose a lot more about what the car will do in that case.
I don't know that, maybe. So the question is, are finite state machines appealing because you can prove more about them mathematically? I assume that's where you're going. Can you? That's a good question. I haven't talked with them